Hello, I'm here today to present to you a paper titled Cooperative Parallel SAT Local Search with Path-relinking. A small introduction before this paper is covered. This research was done as part of a collaboration between Raytheon Technologies and University College Cork. I am Padraigh Jarvis, an intern at Raytheon Technologies Research Centre based in Cork, Ireland. My other author for this paper is Alejandro Arbeláez, who works at the Insight Centre at University College Cork in Ireland. Our email addresses are located on screen right now for anybody who wishes to contact us after the presentation. Now moving on to the topic of the paper. A research question was asked that formed the basis of this paper. That question was, can the inclusion of path-relinking improve the performance of parallel SAT local search? To touch upon parallel SAT, there are two traditional types of parallel SAT solvers. The first, the classical divide and conquer approach, and the second is the parallel portfolio approach. This paper focuses on the parallel portfolio approach, which lets algorithms which are a part of the portfolio compete against one another and then cooperate to solve the problem. The local search process is restarted periodically. When this occurs, each algorithm of the portfolio shares the best assignment of each variable. Here, the best assignment is deduced by the total number of unsolved clauses. Then, instead of starting randomly, data gathered by each member of the portfolio is aggregated to generate a new start state. A pool of elite solutions is saved by each member of the portfolio into this pool here, pool M. Here we see that pool M maintains a matrix of C by N variables, where N represents the total number of variables present in the problem, and C represents the total number of members in the portfolio. Other papers have proposed methods of creating new start states. One of these proposes two methods called prob and pnorm. Prob assigns values to each variable based upon the probability of how many times it was assigned a given value, while pnorm expands this by normalizing the probability function used in prob with the number of unsatisfied clauses. While other methods do exist, these two form the main basis for our comparison for this paper. Now, the focus of this paper is the inclusion of a method called path-relinking when creating new variable assignments. Path-relinking selects two solutions from the solution pool M. An initial solution, also called SI, and a guiding solution, also called SG. The goal of path-relinking is to create an initial variable assignment state that is somewhere between SI and SG. For example, neighbor S1 located here is one step away from the initial solution SI and n-1 steps away from the guiding solution SG. This means the solution generated for S1 will have one variable different from SI and n-1 variables different from SG. Now, for those of you that are familiar with genetic algorithms, path-relinking may seem similar to the way that two parents cross over to one another to create a brand new member of the population. For this paper, we propose 4 methods of selecting an initial and guiding solution. The first one, best to random, selects the best solution from pool M to BSI and a random solution from M to BSG. The next method, cBest to random, selects the solution from the current member of the portfolio to BSI and selects a random solution from pool M to BSG. The next method, current best to cBest, selects the best solution from pool M to BSI and it selects the solution from the current member of the portfolio to BSG. And the final method, best to sBest, selects the best solution to BSI and the second best solution to BSG. In these cases, the best solution is the solution with the lowest number of unsolved clauses. To elaborate more on how each new initial start state is created, a value PD is used. This value balances the trade-off of intensification and diversification. This value can either be between 0 and 1. The value of PD represents the location of the new initial solution between SI and SG. For example, if PD has a value of 0.5, the new starting solution will be equal distance between SI and SG. This means that when creating the new start state, variables have a 0.5 chance to have their value taken from SG and a 0.5 chance to have their variables taken from SI. For all experiments undertaken in this paper, a PD value of 0.5 was used. It is hard to know what the correct value for a PD is without first trying to solve the problem. So a value of 0.5 should, in theory, balance intensification and diversification for all unknown problems. In this paper, we looked at using both SAT and weighted partial MaxSat for evaluating the performance of path-relinking and its proposed methods of selecting SI and SG. For the SAT experiments, 174 satisfiable uniform random K-SAT instances were taken from SAT competitions 2017 and 2018. For the members of the parallel portfolio, 4 different SAT algorithms were used. These are G-squared walk-SAT, pause, adaptive novelty plus, and adaptive G-squared. Each SAT instance was executed 5 times with a cutoff time of 5 minutes. The results of these experiments were then plotted against results from prob, p-norm, the parallel portfolio without cooperation, as well as each SAT algorithm executed sequentially. All of these experiments took place on a 4-core CPU where each member of the parallel portfolio was assigned 1 physical core. In addition, There were two different versions of these experiments taking place. The first version included 4 copies of each algorithm as the members of the parallel portfolio, and the second version used 1 copy of each algorithm as members of the parallel portfolio. The results that can be seen on screen here are the result of the version which includes 4 different members of the parallel portfolio. Here we can see that while non-cooperative appears to take an early lead compared to all of the other methods in finding the highest number of solved instances, at the end of the search time, both current best to random and best to current best overall solves more SAT instances than any other method. When compared to the methods prob and pnorm, current best to random and best to current best solves between 7 and 12% more instances. Moving on to the MaxSat experiments, 123 crafted instances were taken from various annual MaxSat competitions, and an additional 270 uniform random instances were generated. Now, for these experiments, 3 different SAT algorithms were used. These were Adapt Novelty Plus, G-squared WalkSat, and WalkSat. All of these experiments took place in both a 4-core and 8-core setting. However, the results we'll be discussing here are purely in the 8-core setting. These 8-core experiments used 3 instances of Adapt Novelty Plus, 2 instances of WalkSat, and finally 3 instances of G-squared WalkSat for the members of the parallel portfolio. Much like the experiments for SAT, each MaxSat instance is executed 5 times with a cutoff time of 5 minutes. Results from these experiments were compared to state-of-the-art solvers such as DIST, CCEHC, CCLS, as well as the previously mentioned prob and pnorm. One issue that arises from using these solvers, however, is the fact that DIST, CCEHC, and CCLS do not support parallelization. This meant that these 3 solvers had to be executed without cooperation. And as previously mentioned, we can see the results for the 8-core experiments here. On top, we see the results for the 8-core experiments using crafted instances. Here we can see that CCEH finds the most optimal solution to a lot of MaxSat instances very quickly. However, at the end of the execution times, we can see here that best to current best path-relinking method finds more optimal solutions for more MaxSat problems. If we directly compare the numbers to each other, we can see that best to current best path-relinking method finds 13% more optimal solutions compared to EECHEC. Moving on to the random instances, we can see here that for the vast majority of the execution time, the path-relinking method, best to random, finds by far more optimal solutions for the MaxSat instances. In fact, when compared to the best performing non-path-relinking method, we can see that there is a 42% increase in the number of most optimal solutions found when compared to CCLS. Now, to conclude this talk, I would like to answer our initial research question, which was, can the inclusion of path-relinking improve the performance of parallel SAT solvers? From our experiments, we have seen that yes, it can. Over the course of the previously outlined experiments, we found that the majority of cases, there was a noticeable improvement in the number of SAT instances solved for SAT problems and an increase in the number of optimal solutions found for weighted partial MaxSat problems. In some instances, such as the weighted partial MaxSat, we saw a substantial increase of 42% compared to non-path-relinking methods. And just to finish, I would like to give an idea of how we see these path-relinking methods being expanded upon in the future. For all of these experiments and this research, we used a fixed value of 0.5 for PD. As I previously mentioned, without knowing the problem instance ahead of time, it is hard to know what value for PD should be used. As a result, this can be expanded by changing this parameter PD to be an adaptive parameter, where if stagnation is observed during the search process, the value of PD can increase, thus increasing diversification, whereas progress is being made towards an optimal or satisfiable solution, the value of PD can decrease, thus increasing intensification. Thank you for your time. If you have any questions about this paper, please do not hesitate to send either myself or Alejandro an email via the email addresses provided in the first slide. Thank you.